Okay, to start lecture 4. So in the previous lecture we have talked about the mixed strategy as well as the pure strategy, where if you remember what we have covered in the last lectures is that we mainly consider the case where the strategy space is discrete and finite. Okay, so we're gonna consider the case where uh, the strategy space are continuous. So if that's continuous, it's by nature it's infinite, right? Okay. So we're gonna look at the example. Every definition just follows as we defined for the finite case, but probably we need to have some time to make some exercise or look at the example where what is the example of the game or strategic form game where the strategy space are continuous, and then how to compute the Nash equilibrium. Okay. So again, as I mentioned before, continuous the case where the strategy space are continuous, we call it continuous kernel game. That's the kind of the name that the people are using. So in this case, the action or the strategy sets have uncountably many elements. Okay. So for example, if you look at the example that I've showed in the introduction to the game theory lecture, like first lecture, then we look at the example where in mobile, the LTE networks where the terminals are changing their transmission power, and then obviously the power are, I mean, the amount of the power is typically multiplied by the real number, so it should be a continuous. Or kind of access probability, like access probability is within the like interval between the 1 and 0, right, in the Wi-Fi case. So if I increase my access probability, then I aggressively access the shared medium in the wireless network, and then the strategy space is any value between 0 and 1. So okay, even if we have talked about the mixed strategy in the previous lecture, and then it's possible to talk about the probabilistic choice for the continuous case. In that case, we need the probability density function, not the mass function, but we mainly focus on the pure strategy, all right? Just for simplicity, okay? So let me give an example, which is a very famous example in the microeconomics, which is called the Kruner competition. In this case, we are looking at the case where duopoly case. Yeah, the duopoly is in Korean it's a 쌍점 or 복점. I mean, the duopoly market is the market where there are two big giant players or the companies. They want to sell the product. The very nice example is the Coke market, where we have Coca-Cola versus Pepsi, right? I mean, there are very small size of the companies which produces the Coke, but mainly in the, for example, in the USA, we have two big giant players. But we're gonna look at that how they compete with each other, and then economists have studied many models where the Kruno duopoly or the Kruno competition is one of the model. So let's look at what this model is about. So there are two firms like Coca-Cola and Pepsi, and they're producing homogeneous good. It's a Coke for the same market. Now, I mean, if since they are competing with each other, then probably the game theory is one of the useful to look at what they are doing, and the player I's action is a quantity. Yeah, in Korean you can say they're like a 공급량. Okay, so how many bottles or how much that I need to produce, and then let it go to the market. Okay, that's the amount of the good that the company produces. Okay, so in the market, we have Coca-Cola company and the Pepsi company, and they determine the quantity. let's say this is an S1 and S2. Yeah, and every year, like at the start of the every year, they suppose that they determined, okay, we're gonna produce like 100 million bottles of Pepsi or the Coca-Cola. They determine, so that's their strategy. The quantity is their strategy. Now, obviously, the payoff or utility for each player is the function of my quantity as well as my counterpart, the quantity. So in this case, the payoff is essentially should be, because this is an economist, and this should be the total revenue minus total cost. So for example, in the player I, let's say that's Pepsi, and then the strategy of my strategy is S1, and actually, okay, the Pepsi is player 2, and the Coca-Cola is player 1. So like Coca-Cola, for example, the U1 S1 comma S2 is that this is the amount of the quantity they produce, and this is the price that I can sell to the market, right? So that's the price. But the price is, if you look at the price, is the function of my quantity and other guys' quantity, because as we have more and more quantities in the market, then the price will go down typically. That's the basic principle of the economics, right? So that's the revenue. This part is the revenue, and they assume that they can sell everything if they produce like S1 and S2. And then this is the cost, right? And the C is the kind of the unit cost for the one bottle or the one unique quantity. So the CSI is what? Is the total cost of the quantity SI that I produce. Okay? So PQ is the price of the good, which is a function of the total amount of the Q, and the C is a unit cost. Okay? So for simplicity, we're going to assume that the C is 1. Okay? All right? And then somehow we need to model the price function. And we know that, if this is a supplied, this is total supply and this is a price, the basic principle of the economics will, well, if we have more supplies, then the price will go down, right? Somehow we need to model that. So in order to model that, we use this function. So this function is nothing but, this is a price, and this is the Q. It's a total supply, essentially. Then it means that something like this is 2 and this is 0, right? If you look at that, okay. So the price will go down up to this point, and then after that point, price will be, the price cannot be, let's say, a minus, right? Okay, so this is an artificial choice that in order to not to make the price negative, so it's essentially the price function is something like this. Okay, all right. So which means that, well, the maximum price is 0, and the minimum price, maximum price is 2, and the minimum price is 2, and whenever the supplied quantity is within this range, then the price function will follow this curve. Does that make sense? So do you see the situation? Now, obviously, in this case, when we look at that, that's what? It's a continuous strategy, right? Right? Because the strategies are what? SI is in the interval between 1 and infinity. But, well, the Nash equilibrium, everything exactly follows for the finite case. And then in order to look at so I want to solve this problem, meaning that I want to compute the equilibrium, Nash equilibrium, well, if there exists. Okay, so we're going to use, we're going to use the sort of the best response function based Nash equilibrium characterization, where you know what it means, right? So we draw the best response function for the S1, and we draw the best response function and S2, and then we're going to look at the sort of intersection point, and then that's the Nash equilibrium if we have this kind of figure. That's exactly what we have this so far, right? So remember that we define the best response function at this point in this manner, and the Nash equilibrium is defined as the sort of the fixed point of the best response function. Remember, the best response function is a set valued function. So okay, all right. Okay, let's solve that. So how can we solve that? Well, essentially we need to compute the best response. So best response. Now let's think about let's first look at from the perspective of the player 1. So like I need to compute the best response of the player 1, which should be the number the set of the values where S1 and 0 and infinity, and U1, S1, and S2. That's exactly what we have to do. So we probably need to apply this utility function to here, right? And that is equal to the argmax that's S1 P S1 plus S2 minus C is equal to 1, right? So C1, okay? And we know that this guy is on the normal case this is 2 minus S1 minus S2 from this price function. All right, that's a basic second order the equation, right? So S1, let's use blue characters. So S1 2 minus S1 minus S2 minus S1, and we need to maximize this guy. We need to find the S1 which maximizes this guy, and then obviously we differentiate because this is second order equation. We differentiate, and then we get, let's say this is called the F S1, and F dash S1 is let's say 2 minus S1 minus S2 minus S1 minus 1. Okay, you set 1 minus S2 minus 2S1, and we need to find where this value is equal to 0. So S1 should be the 2 1 1 minus S2, and that's the sort of the optimal point, right? So when the S1 is this value, we can optimize this function from the perspective of the player 1. All right, that's pretty easy. So the best response, when we summarize the best response of is 2 over 1 minus S2 if S2 is less than 1. If you draw and 0 otherwise, which means that like if we draw, and this is S2, it's actually S1, and this is S2, and I need to well, I'm gonna draw the best response from the perspective of S2, and then something like this is 1 over 2, and this is 1. And remember, this is the best response curve of S2. And then what? It's a symmetric system, right? If you look at that, if you look at the equation, we can do the same thing for the best response of 2 over S1, and then we can. This is all symmetric, right? So it should be the 2, 1, S1 if S1 is less than 1 and 0 otherwise. Okay? Which should be something like this. And this curve is best response of the player 2 for a given strategy B1. And then Nash equilibrium is this point. And this is symmetric, then how can we compute that? This is what? The curve that the S1 is equal to the S2. So if we compute that, essentially we need to like this curve, and then we put x here. X is equal to this, and 2x is equal to 1 minus x, so x is 1 over 3. So this point is what? Term 3. Where, for example, if S2 is less than 1, then we get this curve, but if S2 is larger than S1, well, it does not go down because of this max function, everything. So we get this, and this is so the Nash equilibrium. S1 is equal to S3. And that's exactly the 1 over 3 and 1 over 3. So the Nash equilibrium is and 1 over 3 and 1 over 3. And we can see that this is what? It's a unique Nash equilibrium if we draw this best response function. Alright? Now in the homework, you need to solve the little bit more complicated of the situation. But mainly you are using this kind of a best response function based characterization. Later, you will see. Does that make sense? Okay, it's basic math, basic algebra. All right. So if the strategy space are continuous, then well, as we do for all other continuous system, we can do a lot of nice, useful mathematical tools like differentiability and everything and so on. Well, for the finite case or discrete case, actually all the problems are sort of the combinatorial problem, right? I mean, the combinatorial problem is very, very difficult. Sometimes, is clumsy to handle. Sometimes because I need to count everything and consider every cases. But in the continuous, well, we can sort of apply all the kind of useful tools which are in the continuous domain, like differentiability and so on. So even for the continuous case, well, sometimes it's easier to solve the game. Okay. All right. Now we're gonna move the issue of the efficiency and the equilibrium selection. So let's talk about what is that. So whenever now we define a game, I mean for the discrete case, for the finite case, or for the continuous case, whatever, right? So we just have some examples where there does not exist an Nash equilibrium, or there exists some there exists a Nash equilibrium and so on. But obviously the question is that does the Nash equilibrium always exist? Because there are some cases where it does, while there are cases it does not. Okay, we're gonna look at the general kind of sufficient conditions under which the Nash equilibrium exists later. But let's forget about don't worry about the existence. Then let's assume that the Nash equilibrium exists, and then, well, it can be what? It can be unique, or it can be multiple. But more importantly, we can ask the question: okay, are they efficient? Okay. I mean, how can we measure the efficiency even? Okay. If we have a multiple Nash equilibrium, which is more efficient? Again, the term efficient is very, very currently ambiguous, right? So somehow the people have some criterion under which that okay, this Nash equilibrium is quite efficient, or this Nash equilibrium is not very efficient, and so on. So how should we quantify this question? Okay, all right. Now, whenever we need to whenever we have to, whenever there is an issue about the efficiency in the Nash equilibrium, well, if you, for example, if you remember the game that we have discussed so far, is something like this guy, right? All right, A, B, C, D. But here the payoff is what? Comma, 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 comma. This number. I mean, look at the prisoner's dilemma. What we are asking is that, well, suppose that this Nash equilibrium is efficient. Well, I mean, this is a Nash equilibrium, and then we want to say that, okay, this Nash equilibrium is efficient or not. Then obviously we need to compare the payoff vector of this guy with the other guys, right? So essentially we need to compare two vectors. We need to. So for example, 1, 3 and 2, 4. We need to compare these two guys. Then obviously the popular notion of the comparing the two vectors, I mean, there are many notions are coming up. Okay, so we first talk about the Pareto efficient optimality. So one measure of the efficiency, whether we are talking about some vector x and y, okay, is a Pareto optimality. So I want to compare the vector x and vector y, like 1, 4 and 2, 5, or 1, 4 and 0, 5. I want to compare these two guys. I mean, there could be many ways of doing that, but one of the popular way of doing is the Pareto comparison, where payoff vector x is Pareto optimal if there does not exist any payoff vector such that this is an element-wise larger than x. All right? Okay? Then we say that it's a Pareto optimal. Does that make sense? So suppose that, okay, I want to claim that, for example, out of these three vectors, all right, I'm asking the question whether 1, 3 is a Pareto optimal or not. Well, let's say, no. I'm asking the question whether the 2.4 is a Pareto optimal or not. Then this should be the y, and then I need to compare the y and here the x, where the 2 is larger than 1 and the 4 is larger than 3. So we are fine. But we need to check all the vectors. And let's compare the 0 and 5 and 2, 4. And the 2 is larger than 0, but the 4 is not larger than 5. 5 is larger than 4. Right? So it's not element-wise this equation. Right? So obviously this is not Pareto optimal. Okay? So when we let's consider all the real number vectors in the two-dimensional. There's a dimension 1 and dimension 2. Let's take A1 and A2. Okay, I'm going to consider all the vectors A1 and A2 which are within this region. Which points are the Pareto optimal point? So this point is Pareto optimal? No, right? Because I can find the point here that is element-wise larger than this guy. So this is not obviously Pareto optimal. Then is this Pareto optimal? No, we can find this point. Is this Pareto optimal? No, we can find this point. So using this logic, if you identify all the Pareto optimal points, that actually all the points that is within this line. So I made a mistake that well, the argument that 2.4 is Pareto optimal. Well, the answer is yes, if we have this only 3 point, right? Because the 2.4 there does not exist any vector such that that vector is element-wise larger than 2.4. Here that does not exist. Okay, so this is a Pareto optimal point, and this is also Pareto optimal point, but this is not Pareto optimal point. Sorry, I made a mistake. Okay, because we are considering three vectors. All right. So going back to this question, as I mentioned before, all the vectors here in this line are Pareto optimal point, because there does not exist any vector that can be element larger than this point. Look at this point, right? And there does not exist that is larger than this vector element wise. Okay? Right? But obviously this is not Pareto optimal point, this is not Pareto optimal point, and so on. Alright? So I mean that's pretty easy to follow. So let's look at the like in this case. This is a payoff matrix of the prisoner's dilemma. Right? Okay? So the Pareto optimality is what? Let's say here, what is the Pareto optimal point? 2, comma 2 is the Pareto optimal point? No, right? Because there exists a vector that is element-wise larger than this guy, 5, 5. So this is not Pareto optimal, but we have these 3 Pareto optimal point. These are the all Pareto optimal point. Why are you talking about the Pareto optimal point? Well, again, Pareto optimality can be used. Well, you may not agree, I know, but can be used a measure of the efficiency, because what essentially it means that the payoffs are sort of large compared to non-Pareto optimal point. Right? I'm not talking about the uniqueness or anything. I'm just talking about the efficiency of the payoff vector. So here in this game, these 3 points are Pareto optimal, meaning that if you compare them, obviously, I mean at our first glance, the 2,2 rather than the 2,2, 5.5, 1,10, 10,1. I mean, seems look larger than 2.2. That's what I mean by Pareto optimal. But we cannot directly compare these two guys, whether which is larger. Well, if you use the measure, okay, so measure 1 for the efficiency. Okay, 1 is the Pareto optimal. Well, professor, I'm going to propose a different measure. You can do that. So what I'm going to propose is that the aggregate payoff. Aggregate payoff is that the summation of the payoff of all players. Sum of payoff of all players. I'm going to use this measure. You can do that. I'm not saying that you cannot do that. You can do that. So if you use this measure too, it's basically the aggregate measure. Then out of for this point, which is optimal, only these 2 points are optimal, right? Because the summation of 1 and 10 is 11. This is 10, 4, and this is 11. So if you use the measure 2, then you can obviously say that, Professor, I'm going to propose another measure. You can do that. Why not? My point is that, well, the efficiency measure can be defined per person. But I'm saying that there exists a common sense measure that the people think that's reasonable, and that Pareto optimality is one of them. That's all the key points that I'm going to mention. All right? Okay? All right? But this is a very let me introduce a very, very interesting story. All right? Do you remember that from the perspective of the efficiency, which are the efficient points? These 3 are the efficient points, right? But what is the Nash equilibrium? Well, the Nash equilibrium is this, which is exactly the opposite. Why this is a Nash equilibrium? Again, we can use the saddle point argument, where we compare here in this vertical line, we compare these 2 guys. So we have this arrow direction. If you this thing and we compare these 2 payoff, we have this direction. Compare this thing, 5 and 10, we have this direction. 1 and 2, we have this direction. So this is a Nash equilibrium point. So what does this mean? in some sense, here in this game, Nash equilibrium is totally inefficient. This is an example of this thing, where the efficiency is from the perspective of the Pareto optimality. So I'm showing you the example where the Nash equilibrium is not always efficient. I mean, even it can be very, very inefficient, which does not contradict with our intuition. Why is that? I mean, what's the game? I mean, think about what the game is doing about. The game is that we're gonna find a situation where how each player will behave if they are totally totally strategically decide their decision. We don't make any effort to sort of the boost up the group rationality. All right, you are rational and I'm rational, so let's work together in order to increase the group rationality. That's not what they are doing. I mean, that's not what we are doing in the game theory. In the game theory, okay, I'm selfish, you are selfish, I cannot talk to each other. I cannot talk to you with you. And then the question is that what kind of strategy will be chosen in this situation, in this strategic situation. So there are some cases where the Nash equilibrium is efficient, but there are some cases where the Nash equilibrium is totally inefficient. And this prisoner's dilemma is one of the examples that the Nash equilibrium is totally inefficient, which is not very surprising because we're talking about game. All right? So people have asked the question that, all right, can we actually make another metric so that what's the difference between when they totally act selfishly and then when they totally cooperate? And that is called the price of anarchy. What is anarchy? Anarchy is in Korean, it's 무정부 상태, right? So if we interpret this word in literally, that means that what's the price of 무정부 상태? 무정부 상태로 시스템을 운영을 함으로써 발생하는 비용이 얼마냐? 라는 뜻이죠. So what's the meaning of the price of anarchy is that what's the cost that we need to pay if we run the system without any coordinator, like government? So price of anarchy is defined as the maximum aggregate payoff divided by the mean aggregate payoff at Nash equilibrium. So for example, here in this case, maximum aggregate payoff is achieved by this and this. So if they cooperate together, and then probably it's the total kind of payoff in the society or in the country can be 11. But since you are working totally selfishly, totally strategically, your equilibrium is 2.2, so the total utility in the society is 4. So let's divide that. So whenever this number price of anarchy becomes larger, then we say that the Nash equilibrium is more inefficient. Does that make sense? Okay. In some books, they switch this guy. So sometimes they use this metric, but it doesn't matter. I mean, it depends. All right. Now, suppose that the price of anarchy is 1. What does that mean? That means we don't need the government. That's essentially what it means. because the society is pretty efficient, even if there is no government. Okay. Sometimes people use this metric price of stability, and that's exactly the same as the price of anarchy, except that we in the denominator we use the maximum aggregate payoff NNE when there exists multiple Nash equilibrium. So, well, in this case, since we have only one Nash, this is a unique Nash equilibrium, right? So in this case, this is same. But in some cases where we have a multiple Nash equilibrium, then this value can be different. All right. All right. So we have talked about the equilibrium selection. What do you mean by equilibrium selection? So why I'm using this word? So in the game theory literature, well, so whenever there exists a multiple Nash equilibrium, even if we didn't discuss that case, well, somehow there should be some mechanism where from which we can select one of the Nash equilibrium. We don't know how to do that, but suppose that you can do that. Suppose that you can choose one of the equilibriums out of multiple equilibriums. Then, what criterion are you going to use? Okay. Again, each people can have a different criterion, but we are proposing some criterion where you can compare the efficiency of the Nash equilibrium among the Nash equilibriums if you have multiple Nash equilibriums. And then again, the efficiency can be quantified by a lot of metrics, but one of the popular way of doing that is the Pareto optimality. Well, another you can use just the aggregate payoff, like you just take the summation between of the payoff of all the players, and then you can choose that, right? Okay, right. All right. Okay. So then going back to the kernel example, we have what? We have proved that this is a Nash equilibrium, right? In earlier case, probably we can compute the price of anarchy of this guy. So in order to compute the price of anarchy, we actually need to compute the maximum aggregate payoff. So the aggregate payoff in this case should be the summation of the payoff of the player 1 and player 2, which is this, right? And that should be the S1. P should be essentially this function. So 2 minus S1 plus S2 minus S1 plus S2, 2 minus S1 plus S2 minus S2. So this is 2 minus S1 plus S2, S1 plus S2 minus S1 plus S2, and then all we need to do is to compute the maximum of these guys. Well, that's pretty easy, right? If we let this is t, then this is a function of ft, and this is 2 minus 2 t, 2 minus t and t minus t, right? So in this case, f dash t is 2 minus t, 2 minus t, and well, let's do that. Minus 1 and t plus 2 minus t minus 1 is equal to, should be 0, right? So here what it's minus 2t, 2t is 1. So t should be equal to 1 over 2. So when it means that S1 plus S2 is 1 over 2, then the aggregate payoff is maximized. is maximized. So if you remember the curve of the best response function, that was something like this, right? And the Nash equilibrium, this was 1 over 2, and this is 1 over 2, it's 1, and the Nash equilibrium was this point. But actually, here, but actually we are, when the aggregate payoff is maximized when we are in this line, when the S1 and S2 is equal to 1, right? Okay, so the price of anarchy, POA, is computed that what's the payoff at the Nash equilibrium? Well, that's 1,3 and 1,3. And what's the payoff? Well, what's the payoff? Well, the aggregate payoff is computed in this way. So in this case, when we this, then essentially it means that f2 over 3, right? It's because it's 1 over 3 plus 1 over 3 here. Because it's 1 over 3 and 1 over 3. And t is what? T is S1 plus S2. And this is what? Is 2, right? 1 over 2. And that's the price of anarchy. And if we compute that and then plug this thing to here, then this means that 2 minus 3 minus 3, and 2 minus 1 over 2, and 1 over 2 minus 1 over 2. Okay, let's compute that. That's what that's 2. Am I doing right? Okay. This is 2. This is 2 over 3. 2. Oh, sorry. I made a mistake. Yeah. Okay. All right. And this is oh, this is larger. What is that? Okay, let me fix what I'm doing that. Yeah, I made a mistake. Come on, what I'm doing. Yeah, this is the 2, and this should be 6. Sorry. And this is 2 over 9. 2 over 9. Okay. And this is 1 over 4. Okay, so that's the price of anarchy. So the price of anarchy is 8 over 9. Still, we need to make more effort in order to remove the government in this case. It's because it's larger than 1. Okay. Yeah. Sorry about the math at the end of the lecture. Okay. All right. So okay, let's summarize that. It's pretty simple. So we have talked about the continuous strategy case, and I show you the example of the famous Kruno competition or Kruno duopoly, and using the best response function, we computed the Nash equilibrium. It's basically the sum differentiation and so on. And then we also have talked about the Nash equilibrium's efficiency. And that is related to the how do we select the Nash equilibrium. Okay, kind of like equilibrium selection. Again, that assumes that we are able to select the Nash equilibrium. Sometimes we cannot do that. All right, so we apply, and then where we have talked about the Pareto optimality, as a one of the measure, but you can obviously come up with a different measure if you like. And then we have talked about the price of anarchy. That's actually the cost that we need to pay without central coordinator or the government. We have also talked about the price of stability, and then we computed the price of anarchy of the criminal duopoly. All right. Now at this point, we have pretty much covered the very, very basic form of the game for the continuous as well as the discrete strategy spaces. Okay. Now there are lots of questions. So the first question is that, well, how can we guarantee or how can we find or prove the existence of Nash equilibrium, for example, or the uniqueness of Nash equilibrium? Right? I mean, well, the game that we have seen so far is a pretty simple game, so we can actually compute or analyze the game and so on, and then we can prove that the existence and sometimes their uniqueness. But if the game is very, very complex, then even we don't know whether the Nash equilibrium exists or not. So there could be some mathematical sufficient condition that can guarantee that the existence or the uniqueness of Nash equilibrium. I mean, the existence and uniqueness proof, it's very, very important and practical. I mean, why is that? Because, I mean, if you can prove that the Nash equilibrium does not exist, then we can predict that, oh, this society is unstable in some sense. Because there is no equilibrium. So, well, each player will arbitrarily choose their strategy. There's no kind of solutions of the game. All right? And the uniqueness means that we're actually really, really stable. Because if we have a multiple Nash equilibrium, it's possible that this guy choose that strategy and I'm choosing a different strategy, because we can have a different perspective. But if the Nash equilibrium is unique, then, well, pretty much we can predict that each player will behave kind of uniformly in some sense. Does that make sense? Yeah. So we're going to talk about that part in the next lecture. I don't know. Oh, I see. Okay. We're going to look at a different form of the game later, which is related to the existence and uniqueness. All right. So please look forward to the next lecture. Now that we are entering into the more and more interesting stories about the game theory. So I'll see you in the next lecture. Thank you.